We're going to begin a study now of a classification of functions we call exponential functions. And exponential functions have the look of y equals a base constant c to an exponent x, where the base is greater than 0. Now, depending on the value of the base, we can get a couple of different looking types of graphs. So let's look at some of the possibilities. We can, as an exponent, use any value of x, any real number. So let's start by graphing y equals 2 to the x. If we let x equal 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the third is 8. If we use negative values for our exponent, 2 to the negative 1 is a reciprocal of 2, so a half. 2 to the negative 2, reciprocal of 4, and 2 to the negative 3. Alright, so if we plot those values, what I'll notice that as I'm going to the left of the y-axis, I'm plotting a half for a y value, a quarter, an eighth. I'll notice that the values of y are getting closer and closer to 0 as x gets more negative. And so what this graph has, one of its features, is it has a horizontal asymptote on the x-axis. And we know that we have a horizontal asymptote because if we take any value of x and put it into the exponent, 2 to anything, even very negative, 2 to the negative 100, would be 1 over 2 to the 100. It would be a very, very small number, but it wouldn't quite be 0. So the graph gets really, really close to the x-axis as we move more to the left. You can check your exponential function in your calculator. Okay, if you trace along, you'll notice that as x gets more negative, the y values get closer and closer to 0. Okay, if we were to graph another exponential function, let's say 3 to the x, okay, the graph goes up a little steeper, but it's increasing. So these are what we call growth graphs, because as x is increasing, the output is continuing to get larger and larger and larger, exponentially. In the case of 2 to the x, twice as large for each one value of increase in x. But we said we wanted to explore the general shape of this graph. So let's take a different value for our base. And so this time I'm going to use a half. And when x is 0, a half to the 0 is 1. A half to the 1 is a half to the 2 is a quarter, and a half to the 3 is an eighth. A half to the negative 1 reciprocates the base, so that's 2. Half to the negative 2 is 4, and half to the negative 3 is 8. And if we plot those points, you'll notice, both from the graph and the table, that the points are a reflection of one another across the y-axis. But we get a graph this time that falls and has an asymptote again on the x-axis, but to the right. And this is what we call a decay graph. And the reason it's falling, of course, is because every time we increase x, we're multiplying by a half, so the values are getting to be half as much each time we increase the value of x. So a half to the x, okay, falls. If we did a quarter to the x, again, we're multiplying by a quarter, so the quantity is decreasing with time. We get a decay graph that's a little steeper, but again, it's falling. So the two major types of exponential graphs are the one that rises, the growth graph, and the one that falls, the decay graph. The other situation that you can have is if you had y equals 1 to the x, which isn't very interesting. That just means that as x increases, y is always 1, and the graph comes straight through like that. Okay, that's really a linear function, and so we will talk mainly about the growth and the decay situation, not usually referring too much to when the value of c is 1, although it can be. Now you might be wondering, why in my table did I not consider values of the base which were negative? Okay, well, you'll notice in our definition of exponential functions, c has been restricted to a positive value. If I were to put a negative value in for c, let me just show you what's going to happen. If I were to make a table out of that, it's no problem to choose values of x. X is 0, produces 1. A value of 1 is negative 2. 2 is positive 4. 3 is negative 8. Okay, so that seems to be just fine. The problem comes when you try to use other values of x, such as a half. If you put a half in to our exponent, remember that means the square root of negative 2, which is undefined. So what happens when you have a negative base is that there are a whole bunch of values of x that are not part of the domain. And so what you end up getting is a bunch of scatter points for values that do work. And the other thing you'll also notice in this case is that the y values are inconsistent. They're positive, they're negative, they're getting bigger or smaller depending on the negative away from each other. So there's no consistent pattern. So just to avoid all of those issues completely, an exponential function is defined for positive values of the base only. Alright, so just to generalize the properties of y equals c to the x, where c is positive, we have a growth graph that passes through the y-intercept of 1. You'll notice that all of the graphs in our example did that. All exponential functions have a y-intercept of 1. And the graph will look like that if c is greater than 1. If we have a growth graph, the graph will fall with an asymptote on the x-axis if c is between 1 and 0. And the more uninteresting situation is when c is 1. We have a linear graph. So some major properties of this graph. First of all, the y-intercept is 1. The domain is all reals. And as long as c isn't 1, the range will be values of y which are greater than 0, and it has a horizontal asymptote on the x-axis, which is the line y equals 0.